Hey, good morning, good afternoon, whenever you're tuning in. We started this class by talking about limits, and we use these definitions of limits and how to find the limit to continue to talk about continuous versus discontinuous functions. So this first part, think of this as a do now, a reteach or a review that leads into today's lesson. So when we talked about limits and reading limits from a graph, there were several key things that we needed to really zoom in on and pay attention to. And I think that some students get confused when a limit will be D and E. And I will say this about limits. There's only one of these on here. Let's call this one A, B, or C. One of these that will be a limit of D and E. So think to yourself, which one of these will have a limit or have a non-existent limit at x equals 1? And if you look here, let's kind of go in order. For this first one, this is the one that has a limit that does not exist. And it has nothing to do with the types of circles or the types of points that are there and open and closed. It has nothing to do with that. It has everything to do with the fact that this left-sided limit from the left of 1 and from the right of 1, we can see that the left is not equal to the right. So in that case, we have a limit that does not exist. And if I wanted to justify this mathematically, what that looks like is the limit as x approaches 1 from the left of that function f of x is not equal to the limit as x approaches 1 from the right of f of x. So when I put some annotations on your work and I put L does not equal R, I wanted you to start thinking about the fact that limits will be D and E when that left and those right aren't equal, or as some people say, the left and the right don't meet. If they don't meet, the limit does not exist. Because that limit tells us what our graph is approaching, and they must be approaching the same output from both directions. And if that doesn't happen here, then our limit does not exist. For part B, let's take a look, and here's how I think of limits again. Is I think about that left and I think about the right. So the left side of 1, right, that's what we're talking about here, the x value of 1, goes up to 2, and the right side of 1 goes up to 2. And it doesn't matter that that's an open circle or a closed circle. Remember that a limit just tells us what we are getting close to. It doesn't matter what happens actually at that value. So in this case, since the left and the right are both approaching an output of 2, then our limit is 2. And if you want to think about this from a kind of math structure, why that is the case is because the left-sided limit is equal to 2. And the right-sided limit of 1 is also equal to 2. So therefore, the two-sided limit as we approach 1 is also equal to 2. So since both of these are equal to 2, that allows me to find the limit regardless of what kind of point exists there. And then lastly, the limit of this part C problem as x approaches 1. And I'm once again just going to mark on here the left, from the left of 1 and from the right of 1. Again, it does not matter what type of circle exists there. So whether there's like a floating point or not, we just care what our graph is doing. And once again, that would be the same exact justification as this over here. The left side is equal to 2 and the right side is equal to 2. So therefore, this two-sided limit is equal to 2. So notice how we can find the limit regardless of the type of point. But if those left and right sides of that x value do not meet up and are not the same, then we have a limit that does not exist. So limits tell us what our graph is approaching. We do not care about the circles. I'm going to clear this, and I'm going to talk about a distinction between that and this. Notice how this is not limits. Limits tell us what we're approaching, while these problems, f of 1, really just want us to know what is the y value at exactly x equals 1, right? So basically to evaluate this, tell me, if you were to plug in 1, What is the y value that is associated to that x value? So here we're actually reading points. We don't want to read the graph. We want to know exactly what that point is doing or what kind of point is there. So if I look at part A here, we'll call this A. And I look at this point, let's see, we have 2 points. We have a filled in circle and we have an open circle. We always want to choose the filled in circle because an open circle actually tells me that there's a hole and this is not even a point. So like no point exists there is what that tells me. Like we get really close to that point, but we never actually get it. So this is no point. We don't want that. The filled in circle is what we want. So we have an x value of 1. What is the corresponding y value? 0. So notice how I don't care what the graph is doing. You could pretty much ignore these red lines and just look for the points and just read the points at x equals 1. So for part B here, let's take a look at this one. And in part B, let's see, once again, I don't have limits. It's just literally telling me at exactly x equals 1. So this is how I have to walk through it. So I have 2 kind of like point looking things. But remember that there is actually no point here for this one. But there is a point here. So therefore, if I were to plug in an x value of 1, the corresponding y value would also be 1. And once again, so a distinction is to really look for that closed circle. Okay, really look for that closed circle or filled in. And then this last one, f of 1. We don't care what the graph is doing. Once again, I need to read the point at x equals 1, the exact, right, y value. So let's look at the x value. Now there is no point here. So let's see, what would the y value be? Some people might be inclined to say 2, but there is no y value because there is no point. Think about that as being a little gap in our graph that actually doesn't exist. There is nothing there. So when I'm asking you, what's the y value at 1? Well, there is nothing at 1. So therefore, this would be undefined. And some people might be inclined to say D and E, but for these, I prefer to say undefined. And that's because there's no point. So a very clear distinction here is between those last problems with limits. We wanted to look to see where those limits meeting, where the left and the right getting to the same point. We didn't care about the circle. And now these, that's all we do care about is the type of circle or point. And we're looking for those closed circles and those y values of those closed circles. So a huge distinction between limits, once again, and I keep repeating myself because this is how I have to organize my thoughts. Limits where I'm actually looking at left versus right, right? And I don't care about the circles, whereas, right, and that's limits because we're approaching. Whereas these next values, we are only looking at the circle themselves. So we would be looking just at the circles. And there's kind of the difference between those two. Now we need this information because today what we're going to be talking about are necessary conditions for a function to be continuous. Then we need to use those conditions to justify whether something is continuous or whether it's not. So really today, we need to understand if something is continuous. Then we're going to use that to figure out and justify when things are not going to be continuous. So we're kind of using a 2-part definition here. So we're going to take some notes. Here are your notes for the day. First is going to be just the definition of continuous functions. And this would be like the definition using limits. So a function, and we'll call our function f of x as we so frequently do, is continuous if, and there has to be 3 different things that need to be satisfied. Number 1, f of a exists. I'm sorry, I should have said f of x is continuous at x equals a. right? So we're actually looking at like any x value, right? So if we wanted to look at the graph at x equals 1 or x equals 2 or x equals 3 or x equals -4, and we want to know if it's continuous there, right? So we'll just say a instead of any number. So f of a just quite simply exists, which means if you needed to evaluate, there is a point there. So I would just say, basically in my own words, a point just simply exists at x equals a. And if you wanted to think about what that would look like, we need at least a closed circle, right? A point, a closed point. Filled in point, a closed circle. I don't know if closed point is a real math definition there. Sorry if it's not. If there is nothing there, then our graph would not be continuous. Part 2, condition 2, it also states that the limit as x approaches a from the left has to be equal to the limit as x approaches a from the right of f of x. So the second condition just means those two limits from the left and right have to be equal. So if we want to think about that, remember with limits, it doesn't matter what kind of circle it is, it just matters where they go. So basically, remember that if the left and right are equal, they're going to meet at a y value, at a point, so to speak. Right, the limit exists is another way to say this, right? Because if the limit exists, then from the left and from the right, it must be the same. And our third condition that must be met here is not only does it have to have a limit, and not only does it have to have a point, but the limit has to actually also be that point at that value of a. So if we take the two-sided limit and actually find where it meets, so let's say it does meet, right, and we have a two-sided limit, it must meet at whatever that value is. There must be a filled-in circle there. So if I think about that, that must mean that essentially the graph meets at a filled in circle, a point. And we're going to get some pictures of what this looks like and what it doesn't look like. And I know this seems kind of weird, but to know what it doesn't look like might be very important. So what it would look like, is we have something moving along, okay? And we'll say that this is our x value of a. And we'll put a little point there, just so we're very clear that that's where it is. This is a continuous function because not only is there a point that exists there, and not only does the limit exist from the same, it approaches the same number from both sides, but that point and the limit are located in the same spot. So that point is actually on our graph where the graph meets. This isn't crazy stuff. It basically just means it's a nice flowing, easy graphic. The graph goes, hits some point and keeps going. It doesn't stop. It doesn't skip over a point. It just flows very fluidly. So there's something that's very important to kind of note here is basically if any condition is not met, f of x is discontinuous. And what we're going to have to do today is actually prove and justify if a graph and when a graph is discontinuous. And we need to know something about the continuous definition to prove if it's not that, right? So basically, if any one of these three things doesn't work, then it's not continuous, it's discontinuous. We're going to take a look at some examples here. So we have 3 different examples. And we're going to state whether f is continuous or discontinuous at x equals 4. And we're going to justify with those definitions from our notes. So the beautiful thing is that left-sided column is actually going to be very beneficial for our justification. So let's look at x equals 4, this first one. And let's actually walk through each one of those definitions. Remember that my first definition just states f of 4 exists. And what I'm going to do here is I'm just going to make a check. Does f of 4 exist? If I plug in a 4, is there a filled in circle there? Is there a y value associated with it? Since there is a filled in circle, then yes, right now, as of right now, it's continuous. But I must check conditions 2 and 3 as well. Remember that condition 2 says the left-sided limit of f of x has to be equal to the right-sided limit of f of x. So according to this graph, do the left and the right equal or come to meet at one point? Yes, they do. Regardless of the circle, they do meet there. So far it's continuous, but we have to check condition 3. Condition 3 says that the limit, the two-sided limit of f of x has to be equal to the actual value at that value, so f of 4. So the limit at 4 has to be equal to the value at 4. I'm going to do this in red. So let's take the 4. The limit is one thing right here, right? Our limit would be 1, 2, 3. But our actual value there, the filled in circle, is actually something different. So I would have something like the limit is equal to 3, but the value of f of 4 is equal to 4. This is not good, right? This does not meet our criteria for a continuous function. So it is discontinuous, and we can now justify why. So it's discontinuous. And here's the beautiful thing. I can use my definition to actually justify this. So it's discontinuous because the limit as x approaches 4 of f of x is not equal to f of 4. So if you think about the reasoning here, really, right? If they're equal to each other, it's continuous, but if anything fails, it's discontinuous. So basically, I just need to show, okay, that third condition doesn't work, therefore it's discontinuous. So I would use that as my explanation here to show that these two things are not equal. Now let's take a look at this next one and take a look to see if we can maybe not do all of this check, but actually just kind of identify just by looking at it. And we can see here, let's see, there's like a little open circle. Is that okay? Well, if I look at my definitions again, let's see, does f of 4 exist? It doesn't, because there is no point there. There was in this last one, it was a floating point, but here there's no point at all. So which condition does that fail? Well, that would be the first one. So this one would be discontinuous because f of 4 is undefined. It does not exist, right? There's no point there, which is that first condition, that f of 4 must exist and it must be defined. Doesn't happen here. There is no point. So even though conditions 2 and 3 are met here, where the left and right limits are equal, I guess that third one actually wouldn't work either. This is going to be our justification. Now let's look at this last one. And let's try to walk through this as well. Let's see. Does f of 4 exist? Yes, there's a filled in circle. So that definitely exists. So condition 1 so far continues. Condition 2, does the left-sided limit equal the right-sided limit? Let's see. Does my left equal the right? Absolutely not. So there, right there, is the reason why it's discontinuous, because that second condition is discontinuous because, and I can literally use my definition, the left-sided limit, except I'm not going to use a, I'm going to say 4 of f of x is not equal to the right-sided limit at 4 of f of x. So once again, you can see, okay, for this first one, if the limit was not equal to that value, and that would make it discontinuous, right? That fails a kind of continuous test. For the second one, what failed a continuous test was the fact that there is no point there, condition 1. And then this would be like condition 2 here, where the left and right aren't equal. So these are all kind of 3 distinct examples of functions that are discontinuous. Remembering that continuous would just kind of go to that point and then carry on. So if you were to think like, okay, for this second one, if you were to fix this second one to make it continuous, all you would need to do is just fill in that point. And then all of a sudden it would be continuous. But in that case, it's not the case. Okay, so these are our definitions or our conditions that need to be met for something to be continuous or in some cases discontinuous. And what you now have to do is go to that Desmos and take a look at those graphs and test yourself. Can you identify where a graph is going to be discontinuous, where one of these 3 things is going to happen? And then can you justify it? Can you justify it mathematically with this kind of structure and language? If you can do that, then you can kind of prove your understanding and have that kind of very math-specific presentation that is so needed to basically win an argument in mathematics. Okay, go to that Desmos, make sure you have these notes down, and I'll see you in class.